Today's lesson, beginning in chapter 11, is on reflections, translations, and translations, reflections, and rotations. Sorry about that. So the first thing, we're just going to talk about translations. And we need to state the coordinates of P prime. So if P is negative 4, 4, right? That'd be negative 4, 1, 2, 3, 4, positive 4. There would be P. If we move P 2 units down and 2 units right, that would be P prime. Okay? And that movement right there is called a translation. 2 down, 2 to the right. Okay, let's say P is negative 3, negative 2. Then we want to move it 3 units right and 3 units up. It would be moved to there. That's called a translation. The 0.22, let's say that's P. We're going to go 2 down and 2 right. That would be P prime. Those are called translations. Okay? Reflections. Negative 5, 3. 1, 2, 3, 4, 5. 1, 2, 3. Here's P. If we reflect this on the y-axis, then it would be 1, 2, 3, 4, 5 units from the y-axis. So if we fold it over on the y-axis, there would be P prime. Okay? Negative 4, negative 3. 1, 2, 3, 4. 1, 2, 3. There's P. We're going to reflect it again on the y-axis. So that's 4 units away on the y-axis, so there's P prime. Okay? Negative 1, negative 5. That's down here. 1, 2, 3, 4, 5. So there's P, but we're going to reflect it on the x-axis. Well, that's 5 units down from the x-axis. So we're going to go 5 units up to reflect it on the x-axis. There, so we have translations, we have reflections. The last part is rotations. 4, 2 is located right there. There's P. We're going to rotate that 90 degrees. Okay? So we're going to, let's see, I like what's called the hook method. So we're going to go right 4 up 2. So then to go 90, we're going to go right 4. Instead of right 4 up 2, we're going to go 1, 2, 3, 4 up 2, 4, left 2. We're going to go counterclockwise that way. That's 90 degrees. So there's P prime. See how it rotates? Okay, 3, 0. 1, 2, 3. Let me erase this. Hard to see. 3, 0 is right there. We're going to go 90 degrees. Well, if we just rotate that 90, P prime would be right there. What about 6, 0? If we rotate 180, it'd be 1, 2, 3, 4, 5, 6 units there, and that's P prime. And we'll get into more of the algebra that is required there. Okay, now vectors. So the diagram here at the right shows vectors. PQ. That's a vector PQ. The horizontal component is 5. The vertical component is 3. This is our initial point, P. This is our terminal point, Q. Well then, if we write this in component form, literally the vector PQ is 5, 3, which means right 5, up 3. Okay? That's a translation. This is called a translation. We're just going to write it in vector form. So in the diagram, name the vector and write its component form. Well, the vector starts at J, ends at K, so this is vector JK. Now, what are the components of vector JK? Well, we would go right 3 and up 4. 1, 2, 3, 4. So the vector is 3, 4. Now, if you get into pre-calculus, we'll take it a step farther, but I like this component form very nicely. So translations, if you think about it, is nothing more than a vector. So if we had this point PQ, or this line segment PQ, and we were going to slide it or translate it this direction, the vector then can be seen here and here, but it's the same vector. So we would go right a number of units and up a number of units. So what we do then is we would add the constant to the x value and the y value. Now, if we went the other way, obviously, you'd subtract it. Or if we went down. So the vertices of triangle ABC are A is 0, 3. So there's A. B is 2, 4. And C is 1, 0. There's our triangle. We're going to translate it using the vector 5, negative 1, which means right 5, down 1. So I'm going to take point A first. We'll use a different color. So point A would be right 5, down 1. There's A prime. B, right 5, down 1. B prime. C, right 5, down 1. C prime. So there is our triangle that has been moved via the vector 5, negative 1. And if you drew every vector here, the vector would be right 5, down 1. Kind of cool, isn't it? Okay, what's the rule for this translation? We'll look at A, then A prime. This is A. This is A prime. So we're going backwards, right? So we're going left, 1, 2, 3, 4, and up 1. So the vector would be negative 4, 1. Left 4, up 1. Does that work for B? Yep. Does it work for C? Yep. So that is the rule. We call that a rule. Now, the translation postulate simply states that it's a rigid motion. Rigid means it maintains the same size and shape. Okay? So it maintains congruence, in other words. It does not change the size or shape. Now, 2 or more rigid motions is a rigid motion, which means we could do 2 of those, but that would mean that it would still be a rigid motion. It would still be the same size and shape. It may not look the same direction-wise, but it would be the same shape and size. Now, reflection, we simply have a reflection line. You're the same amount of distance away from the line, and distance is always measured perpendicular. So we always measure distance 90 degrees. So the line of reflection actually goes through the midpoint. So if we graph triangle ABC with vertices 1, 3, 5, 2, 1, 2, 3, 4, 5, up 2, there's B, and C, 2, 1, and here's our triangle, and we reflect it in the line x equal 3. Well, x equal 3 means we have a vertical line at 3, at x equal 3. So we are simply going to reflect it there. Well, how far is A away from this line? 2 units. So if we fold it on that line, there's A prime. How far is B away? 2 units, right? 1, 2, so 1, 2, there's B prime. How far is C away? 1, there's C prime. Draw your triangle. That would be the reflection at x equal 3. Pretty cool. Now, if we do the same triangle. There's A. B was 5, 2, 1, 3, 5, 2, 1, 2, 3, 4, 5, 1, 2. There's B. And C is 2, 1. And we're supposed to rotate this or reflect it at y equals 1. Well, y equals 1 is a horizontal line. Well, if we do that now, the C is not going to move because it's right on the reflection line. B becomes B prime here, and A becomes A prime here, and there's the reflection on y equal 1. Pretty cool, isn't it? Okay, now the general rules, and this is really nice, actually. If we reflect it on the x-axis, all we do is make the y negative. If we reflect it on the y-axis, we make the x value coordinate negative. Okay? If AB is reflected in the line y equals x, then we simply just interchange A and B, or x and y in this case. And if it's y equal negative x, it's the opposite and reciprocal. We switch them. So, I didn't get that in a good place, did I? Okay, well 6, that doesn't work very well. We'll see if we can make this work. J is 1, 3, hope we can see this. K is 4, 4, 1, 2, 3, 4, 1, 2, 3, 4, there's K. And L is 3, 1, so there's our triangle. Okay, so now it says, graph it and its image after reflection in the x-axis. Well, if you just look at these, we don't even have to graph it, okay? We can literally figure out what the new points will be just from this. If we reflect it on the x-axis, we negate the y. Haha. So instead of 1, 3, J prime will be 1, negative 3. Instead of K being 4, 4, K prime will be 4, negative 4. And L prime would be 3, negative 1. Now let's see if that is what happens when we truly reflect it on the x-axis. So there's L prime. 4 down, 1, 2, 3, 4. There's K prime. And he's 3 away, old J, so J's going to be there. Connect the dots. There's the reflection on the x-axis. Okay, is the point 1, negative 3 for J prime? Yes, it is. K is 4, negative 4. K prime is. And L prime is 3, negative 1. Hey, cool. It works. Now it says, let's reflect it on the y-axis. Okay, if it's reflected on the y-axis, we negate the x value. So now I'm going to go double prime on these because we've already reflected it once. I'll do it down here. So J double prime, we are going to negate the x. K double prime, negate the x. L double prime, negate the x. The y does not change. Well, if I reflect this on the y-axis, J prime should be there. K prime should be 4 over 1, 2, 3, 4 at the same depth, or K double prime, sorry. And L double prime should be 3, 1, 2, 3. Can't really see that, I apologize. I thought I cleaned this up, I guess I didn't. So are those points coincidental with those? Is J double prime negative 1, 3? Yes. Negative 4, 4? Yes. Negative 3, 1. So we don't even have to graph them. We can figure out the reflection if we know the x and y axis are the axes of reflection. And a reflection is a rigid motion because it keeps the same size and shape. Along with it then, we have this word called symmetry. Symmetry just means we can cut it in half and fold it in half. Now, these are all hexagons, 6-sided figures, okay, 6-sided polygons. How many lines of symmetry does A have? It's got to fold completely over. I think that's it. Oh, nope, you're right. Because I know some of you saw this too, right? I think there's two. The diagonals won't work because they won't fold correctly. Now B, I think we got a bunch. Okay, there's one, there's one, there's one. Yeah, there's one, and there's one. I think that's it. So 3. How many we got? 1, 2, 3, 4, 5, 6. 6 and 2. How many on C? 1 in there. Okay, so those are called lines of symmetry. Okay, how about the lines of symmetry of a rectangle? 1, 2. If I do the diagonal, are they going to fold over? The answer is no. So that's it. Vertical and horizontal. Pentagon, number 13. Well, we got this one. 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 Yep, that's it. I think there's 5. And it looks like this triangle would be here, and that's it. Right? I think that's it. I think there's only one there. 14. Okay, now rotations. Now rotations, as you can see, here's a rotation of 40 degrees. We usually rotate it around a point. Okay, a point of rotation. Now, this is very important. As you go through every 90 degrees that you rotate it, you flip your points and negate the first one that's flipped. And that's all you do. So basically, if I had the point, here's an example. Let's say I had the point 3, 4. So over 3, up 4, and it was this point right here. Then a 90-degree rotation, I would flip these two numbers, X and Y, and negate the first one. So that would be a 90-degree rotation. 180, I would flip them again and negate the first one. Okay? So now it's -3, -4. If I go a third time, 90 degrees, I would flip and change the sign. And if I went 360, which is back to the original, I end up back at the same place. Okay? Pretty cool. Pretty cool concept. Okay, so we're going to graph the quadrilateral. 3, 1. There's R. S is 5, 1. There's S. T is 5, -3. And U is 2, -1. And we're going to rotate this 270 degrees. Now, I'm just here to tell you that you would not want to do this by hand. Why didn't this work? There we go. You would not want to do this by graphing. It's just not very nice, okay? But we can do it using the points. 270, we're going to do it 3 times, right? 3 times. So I'm going to start with R, 3, 1. The first rotation is 90 degrees. That's going to be -1, 3. R double prime, so that's 180, would be -3, -1. Flip the X and Y and negate the first. Change the sign to a negative. When I re-flip it again, that -1 becomes +1. So our R triple prime here would be 1, -3. Let's do S, 5, 1. 90 degrees, -1, 5. 180 degrees, -5, -1. 270, S triple prime, 1, -5. Do you see a pattern between these two? I do too. So R triple prime is 1, negative 3. S triple prime is 1, negative 5. I bet you can figure out T. Let's see. We flip them and negate the second one, right? Looking at the pattern, 3, 1 is 1, negative 3. 1, negative 5, negative 3, negative 5. And then U triple prime would be negative 1, negative 2. So 1, negative 3 would put us here. There's our triple prime. 1, negative 5 would put us there. That's S triple prime. U's negative 1, negative 2. And T is negative 3, negative 5. 1, 2, 3, 4, 5. And there you have it. There's a 270-degree rotation. I like using the equations better. Okay, so 3 zeros J, 4 3 is K, and 6 0 is J, is L, I mean. So if we're going to do a 90-degree rotation, guys, again, all we're going to do is flip them and negate the first one. Well, there is no negate. It's 0, 3, because you can't negate 0. Negative 3, 4, it should be prime, and 0, 6. So if we rotated this correctly, J would be here, J prime, K prime would be negative 3, 4, and L would be 0, 6. And guess what? There it is, at 90 rotation. And we used the rules, because the rules are much better to work with. Rotation keeps the shape the same, so it's rigid. Now, how many of these have rotational symmetry? In other words, if you rotated it, you could get it to look like it without going all the way around one time. Well, if we rotated this 180 degrees, it would look the same. How about an octagon? Well, that would be what? We could rotate it each, like right there, right there, right there. What's 360 divided by 8? So that'd be 45 degrees. So every 45 would be the same. This trapezoid does not have any. None. No rotational symmetry. Would not look the same. Does this rhombus? Oh yes, every 90 degrees. How about this thing? Yep, every 90 degrees. How about this right triangle? Nope. Okay, that concludes our lesson 11.1 through 11.3.